Yes, class, is this audible? In the last class we had completed LCR circuits. So today we'll start with power and energy of the LCR circuit. So see, we'll first calculate the average power. We do not calculate the instantaneous power. But to calculate the average power, we have to have the values of instantaneous power. What's the formula of power in terms of voltage and current? Yes, class. What's the formula of power in terms of voltage and current?
P is equal to VI.
P is equal to VI. Yes, from there only we'll start. So see, instantaneous power will be what? Instantaneous power. This power's formula is V into I. So V, or let's write it in terms of EMF, E into I. So E was what? E was equal to E naught sine omega t. So here also power will be equal to E naught sine omega t. And current will be, see, current was what? I naught sine omega t. But we had this phase difference as well along with it. So we'll write down the phase difference here. Sine omega t minus phi. Now from here, write E naught and I naught together. Here sine omega t minus phi. This much is left. Now see class, if I multiply and divide it by 2, there won't be any difference in it. If I multiply and divide it by 2, see, this cancels and it becomes 1. So if I multiply it and divide it by 2, in the denominator there will be a 2 and in the numerator there will be a 2. Sine omega t minus phi. Now from here there's an identity. Does anybody know this? 2 sine A sine B, how do we write this? Any idea?
Cos A plus B plus cos A minus B.
Yes, cos A minus B minus cos A plus B. This is cos A minus B minus cos A plus B, right? So the same identity we'll be using here as well. So if you substitute this identity, so the average power that you'll obtain, now you'll get the average power. Average power, we are calculating what? Average power dissipated per cycle. So average power will be what? Average power will be the average of it. Before that, let's write the power, instantaneous power. Let's put it into the identity. So if you put the identity, this becomes what? The instantaneous power becomes E naught, I naught divided by 2 will remain here only. And rest you will get cos phi minus cos omega t minus phi. How did I get this? By putting everything in this trigonometric identity. Now, this is the instantaneous power's value. If I want to find out the average power will be average of this whole term, average of E naught, I naught by 2, cos phi minus cos 2 omega t minus phi. This whole's average will be actually the average power. So see, whenever you have this second cosine term with you. So second cosine term is time independent. So average of it over a cycle is always 0. So this term will be 0. Why? Because this is second cosine term. Now, reason of it, you need not go into the details. You just have to remember 2 things over here that are related directly from your maths. One is this identity. You can rote learn it. Nobody's going to ask you to derive it or why did you use it directly. Just mention in the bracket whenever you use it in your derivation. Because this question comes to show that or derive the formula for power, derive an expression for average power of series LCR like this. And then this is second cosine term is 0. You need not even mention this. You can directly say cos 2 omega t minus phi is 0. This you can write second cosine term. This you can write just for yourself. So how much is left? So power average becomes what? E naught, I naught by 2, and only cos phi is left. Now tell me one thing, class. If I multiply root 2 into root 2, what would I get?
2.
2. Yes, Hamza, it will be 2. So it means I can write 2 as root 2 into root 2. So power average here becomes E naught I naught cos phi is there. Instead of this 2, I'll write it as root 2 into root 2. Now, can anyone tell me what is E naught by root 2? E naught by root 2, peak value divided by root 2. What is this? Yes, class, E naught by root 2. Akifa, what is this term that we are obtaining? E naught by root 2. Krishna,
Ma'am, ERMS.
ERMS exactly. So why you people weren't answering? ERMS, definitely it will be ERMS. ERMS is E naught by root 2. IRMS is I naught by root 2. This is the very basic thing, class. I hope you are aware. I have told you about your test on 8th. I'll take your test. It's on next Thursday, right? So please prepare for it. This value is ERMS. Similarly, if you look at this value, I naught by root 2, this becomes IRMS. So what's the formula of power that you're getting? Average power is ERMS multiplied by IRMS into cos phi. This is the formula for average power. So you will be getting average power only. Certain special cases we'll see, 2 cases at least we'll see before we discuss certain things. But just note down till here. And this question comes in the board to show the value of power. Here the additional things are just 2. From mathematics, one is this and other is this. So you just have to directly write it. No need to give the explanation. Just write the identity in the bracket somewhere on your sheet and write that cos 2 omega t minus phi is 0. Nobody's going to ask you the reason for it. See, so formula of average power is what? ERMS, IRMS into cos phi. And cos phi is what? Phi is your phase difference. Phase difference means the angle that is there between the voltage and current. Now, in case of pure resistive circuit, what was the phase difference, Hamza, between voltage and current? In case of only resistor containing AC circuit. Hamza. Fatima? Phase difference between current and voltage. Have you all stopped revising or what? No, Akifa. Wrong answer. Exactly. Now it's right, Hamza. Both are in the same phase. No, Sarah. Both are in the same phase. There is no phase difference in a circuit containing only a resistor. For a pure resistive circuit, there is no phase difference. So phase angle phi is 0. If phi is 0, cos phi will become what? Cos 0, it will become 1. So here in this formula, P average, when you will put IRMS, ERMS, cos phi, you will get power average as IRMS, ERMS only. So this will be the maximum value. And class, please revise. Start revising. Have you all not studied AC? Are you not doing it simultaneously? Who all have actually studied this lesson? See, if you do not study the phase difference and all these factors, you will not be able to remember at the end, because you have not only the single chapter AC, you have multiple chapters with you. So at the end, it will become very confusing for you. Whether this was the formula, you don't even need to rote learn all the things. You just have to remember which quantity is leading what quantity. So according to that, you will just have to add minus pi by 2, subtract minus pi by 2 accordingly to it. I have told you several times that if you do not study simultaneously in alternating current, then things will become confusing for you. Now, for circuits having only capacitor or only inductor, if it's a pure capacitor or pure inductive circuit. So here is the phase angle between them, 90 degrees. Right, class? Here, so Sarah, what you were mentioning, 90 degrees, here it will be valid. One is leading, in one case voltage is leading, other case voltage is lagging, that's a different thing. But phase angle will be 90 degrees only, pi by 2. So cos 90 degree will give you 0. So here, P average, if you put, this will become ERMS, IRMS into cos 90 degrees. So this term will be 0 simply. So power average is 0. So these two factors, these two portions, these won't come in your numericals. These will come in your theoretical questions in such a way. Discuss the various special cases for average power of L series LCR circuit. So you can write these 2 points if it's for a 2 marker. In detail, you can just add 2 or 3 lines by yourself that average power for pure capacitive or pure inductive circuit is 0. And why did you take 90 degree? You can mention that voltage leads current in case by 90 degree. In case of capacitor circuit, current leads capacitor. Like this, you can mention these 2 lines, or both are in the same phase. So that's why phi is 0 degree, and all these according to the marks and weightage. Or it can be directly asked in your very short markers, 1 markers, what's the average power for pure capacitor circuit? So you don't have to mention there that the average power is IRMS, ERMS. You have to directly say that average power is 0 for all the circuits. Fine. So remember this conclusion for it. All right, class. And one more thing. Yes, this cos phi that you are obtaining, P average, ERMS, IRMS, and here we are getting cos phi. So just look at this cos phi. this is known as power factor. So whenever in your questions power factor or any question regarding power factor is mentioned, so just understand that power factor is your cos phi only. So it may happen that the rest of the full question you are aware of, you just have to, they are just asking you what's the average, what's the power factor. So don't get confused by any other term, it's only cos phi, which is usually written as R by Z and it can be calculated in any manner. So power factor for purely inductive and capacitive circuit is 0. Because cos phi is 0. So cos phi is 0. It means power factor is 0. So for a purely inductive or capacitive circuit, power factor is 0. Fine. This point you have to remember. And one more thing, class. When the average power is 0, like in these cases for inductive, for capacitive circuits. So whenever your average power is 0, you call the type of current that you obtain, no, you call it as wattless current. So now again, in your short answer questions, it can be asked, what is wattless current? When is the current in an AC circuit wattless? So I just mentioned that point, don't worry, then you can note it down. Wattless current is basically what you know, what is what? What's the SI unit of power? WATT, not WHAT. What? This. So wattless means no power. So from here only you can identify. So wattless current. This is what? The current in AC circuit. The current in AC circuit is said to be wattless if P average, or let's write it in words only. If the average power consumed in the circuit is 0. And you know the cases. When will it be 0? This is when your P average is 0. Simply, this is known as wattless current. All right. So if this term is written somewhere, just connect it. Note down from here. Okay, Akifa, you can join after a few minutes. See, when we were doing electromagnetic induction, I think we had done this. Energies expression, energy stored in an inductor. Just let me know if you have not done. So energy stored in an inductor. This is half L I square. This is the energy that is stored in inductor. Similarly, energy stored in capacitor, we have done half CV square. We have done half Q square by C as well, and half QV also. These are the energies formula or expressions for energy stored in capacitor. So these are the two energies. So these are what kinds of energy? These are the energy that are present in the individual circuits. Individual circuits means it's if only resistor, if only capacitor is given, or if only inductor is given. Now, average power for a pure capacitor circuit and pure inductive circuit, that we know. What is it? It's 0. Right now only we have discussed that cos 90 is 0, so it will be 0. But in your exam, you can get a question to prove this. Why is it 0? And you obviously cannot write because cos 90 is 0, that's why you are getting it 0. You have to derive the whole expression that yes, your power is coming out to be 0. I have just written these 2 points for inductor and capacitor's energy because it may happen that you will be needing these to use them in your numericals for this lesson as well. But rarely this is used in their respective lessons. Now, if your, let's say average power we are calculating, so expression for the average power. So yes, class, let's take the example of any, let's say if it's a capacitor. So E will be equal to what? E naught sine omega t. And current will be equal to what? See, current leads in case of circuit containing only capacitor. Revise all those things. So here what will happen? This will be I naught sine omega t plus pi by 2. Plus pi by 2. Fine. So using the identity, you can write this as I naught cos omega t as well. This also you can write. Now the formula for work done. dW is equal to what? dW is equal to power. Power is what? See, power is equal to work done divided by time. So from here you can write, if power is work done divided by time, you can write down that your dW means the work. This is power into dt from here. Fine. So dW is speed into dt. And power is what? Power is I naught E naught divided by, or you can say sine omega t cos omega t. E naught sine omega t, I naught cos omega t. I have written these separately because these will be used together for the purpose of integration. And then dt, definitely. So dW is equal to power. This is power. This is time. Fine. Now we have to find the formula for it. So sine omega t cos omega t can be written as sine 2 omega t. So let's write it in terms of this first. This is I naught E naught sine 2 omega t dt and 1 2 over here. Now see, average power we are calculating. So for average power, we'll integrate this. We have the time. If we integrate it from 0 to t, we'll get the average power for it. So average power per cycle, if you write. For average power, we need work done divided by time. This will give me the average power. 1 by time over here. What is the work done? Work done is dW from 0 to t. Now you put in the value of dW, what you have derived. So power average will be what? 1 by t is over here. dW is what? dW we have calculated. This is I naught E naught by 2 sine 2 omega t dt 0 to t. All right, class. This much is clear to all of you? Till this, now just integration is left. Clear? Yes or no?
Yes, ma'am.
Okay. Now, see, we just have to integrate this from 0 to t. Time period, we have chosen it as t. So, put all these things together. Power average will be what? This will be E naught I naught divided by 2t. Now, when you'll integrate sine 2 omega t, you will get firstly a negative sign for cos. And you'll write 2 omega t. And 2 omega is the constant. So, it will get divided in case of integration. And limits are from 0 to t. Now CP average will be what? Put this minus sign with them. Minus E naught I naught by 2t And not only 2t, you can even write 2 omega as well. So 2t into 2 omega gives you 4 omega t. And here what is left? Cos 2 omega t into t. Cos omega t minus cos 0 degrees, right? So from here, Sneha, what's the relation between omega and time period? How do you relate it? Sneha Manoj? Time period you have and angular frequency omega is there. How to relate it? What's the relation? Yes, Sneha? Kulsum? Omega and capital T. How do you relate it?
Omega is equal to 2 pi t.
2 pi by t. Yes, 2 pi divided by t omega. Omega is 2 pi t. Not 2 pi multiplied by t. It is in division. Omega is actually 2 pi nu. So instead of frequency, you can write 1 by time period. This is the formula. Fine. So this becomes cos 2 omega is 2 pi by t into t minus cos 0 degree. See class, tt gets cancelled from here. Now you have your answer ready. What's the average power from here? Minus E naught, I naught, 4 omega t, leave whatever is over here. This is cos 4 pi minus cos 0 degree. This is also 1, this is also 1. So average power becomes what? Minus E naught, I naught, 4 omega t. Cos 4 pi is 1 minus cos 0 is also 1. This cancels, gives you 0. So this is a proof. And this question can be asked. Prove that an identical, or you can say prove that an ideal inductor connected to an AC source does not dissipate any power. In this way, it can be asked, or it can be asked, prove that an ideal capacitor connected to an AC source does not dissipate any power. So you will mention, and you have to tell when an AC is applied to a capacitor, current leads the voltage in phase by pi by 2 radian. Then only your proper results will be valid. And when you will be able to write the statement, when you study and when you know the fact that actually current leads the voltage by pi by 2 in case of capacitor. Similarly, for inductor also, if it's there, you will say when AC is applied to an ideal inductor, current lags behind the voltage in phase by pi by 2 radian. So you can write over there, see answer, derivation, everything will be same. It's just that you will be getting minus I naught cos omega t. But once, so what will happen ultimately, this minus sign that you're getting, this won't be here. Rest of the derivation will be exactly the same. So this question comes in exam and it's an important question. It's more important than the derivation of average power. And do note these 2 points as well, because these will also be used somewhere or the other. Clear or not? Except
Clear,
for
ma'am.
Krishna and Atif, only these both have been responding. Huzaifa, Hiba, Hamza, did you understand? Fatima, could you follow up?
Yes, teacher.
All right. So any doubts, just note it down. If you have any doubts, ask me. Now what about your half yearly class? Now schools must have started, no? First. Any idea when is your half yearly exam starting? If you people get the idea, no, just let me know what's the syllabus coming, because we have to have the revision classes also. So revision classes we'll have according to everyone's exam and syllabus. I think most probably maximum till EMI it should come in your exam. Yes, answers. Submit your answers in the chat box. This is a very easy question. It's a question actually from your NCRT only. Question is very, very easy. All of you try Akifa, Atif, Fatima, Josefa, Krishna. Yes, Sarah. Correct. Kulsum also try. Sneha. Last 1 minute and I'll discuss it. But at least all of you try to submit. The question is very easy. Power is given, ERMS is given. You just have to relate it. Yes, Akif, the first part is correct. Good. Correct, honey. So 3 students have already answered. Akifa, Sarah, and Hanifa. See, let me discuss it. Power that is given is 100 watt. And this is ERMS value given to you, 220 volt. First part is saying resistance of the well. So normally also, what's the relation between power, voltage and resistance? We write it as P is equal to V square by R. So here also resistance will be equal to what? ERMS square divided by average power. You'll just convert it in terms of AC. Second question is also correct, Akifa, and first part is right answer. Good. So the resistance can be written like this. So this is what 220 into 220 divided by 100. This becomes what? This is 22 into 22, 480. So first part is this one, 484. Yes, Hiba, 484. Now peak voltage of source. Right now only we have discussed what's the relation between peak voltage and ERMS. ERMS will be simply root 2 ERMS is E naught divided by root 2. From here, E naught can be written as root 2 into ERMS. Root 2 is 1.414. ERMS is given as 220. Second answer, 311.142. Yes, yes. Just add the unit answer. So into ERMS is 220. This will be approx 311 volts. Last part, IRMS. Did anyone calculate that? IRMS? Third part, yes. So all 3 parts are correct. Akifa has answered all the 3 parts. IRMS will be what? See, in general, yes, last part is correct. Current is written as power divided by voltage, P is equal to VI. So here IRMS will be written as VP average divided by ERMS. Power average is 100, ERMS is 220. This will be 2, you'll have 5 and then 11. So that will be 0.4545 something. No, so it should be around 0.45 amperes. This much. So all those who have not done, just note it down. Then we'll take a break of 5 minutes. Then we'll start with a new topic from this lesson. 2 topics are left now: LC oscillations and AC transformers. Transformers and LC oscillation. Only this much is there. So I think all those who have written, it's fine. Those who have to write it down. It's 7:32 over here. No? So I'll start after 5 minutes. All right, class. Let's start with it. Are you all here? So let's start with LC oscillations. This is also an important topic, but from here, first understanding of why are we saying oscillations are occurring in LC circuits, that is also important. So LC means what? LC means inductor is there and a capacitor is there. So see, let's see a circuit. This is an inductor and this is a capacitor. Fine. Now current, this is inductor, this is capacitor. At this moment, current here is 0. So see, a capacitor initially has, let's say, Q naught or in some amount of charges it has. Fine. And it is connected to an ideal inductor. This is the story right now. Now, electrical energy stored in the capacitor. Right now, I told you, no, we had discussed the energy for capacitor and energy for inductor. Here it will be used. Energy stored in a capacitor will be what then? Half Q naught square C. This will be half Q naught square divided by C. So there will be a certain energy. This is UE, this is UB, magnetic field, and this is electric energy. Electric energy and magnetic energy. So what happens? The electrical energy is stored in the charged capacitor. And this, since there is no current in the circuit, energy stored in the magnetic field of the inductor is 0. So here this is 0 and here this is at its maximum value. Now let's see certain modifications that will occur. Now what will happen? As the circuit is closed, when your circuit is closed, the capacitor begins to discharge itself through the inductor. From here, certain I current is flown. This is the inductor, this is the capacitor. Let's say this is the positive plate of it, this is the negative plate. So it begins to discharge charges. So current flows, capacitor does what? It begins to discharge itself through the inductor. So it causes the current I to flow. Now as the current I will increase, it will build up a certain magnetic field around this inductor. Initially, this magnetic field was not present. Now it is producing certain magnetic field here. So magnetic field will also exist, whereas electric field will also exist. Now, let's see further what will happen. Now, what kind of energy was there in the capacitor? In the inductor, it was half Li square. So initially in the capacitor, it was half Q square by C. Then it began to discharge itself, and because of the presence of current, there was magnetic field, and so the magnetic energy came, and energy stored in the inductor was half Li square. Now, at a later instant, what happens? Capacitor gets fully discharged. This is, let's say, this is your circuit. So now the capacitor initially, which was discharging itself, when it will start discharging itself, at the last, what will happen? All of the current that it is containing, all of the charges that it has, it will vanish. So all the current has, though it has gone through the inductor. This is the inductor. But now the magnetic field lines and the intensity of magnetic field, this will increase. Because this has discharged itself completely. So electric energy won't there, but regarding magnetic energy, you will be having a magnetic energy. What happened over here? At a later instant, capacitor gets fully discharged and potential difference across its plate becomes 0. So current reaches its maximum value and energy stored in the magnetic field is what? Half Li square. Thus the entire electrostatic energy of the capacitor has been converted into magnetic field energy of the inductor. All of the electrostatic energy which was present, now you can see there's a shift. Initially we had started from here and this was 0. Now magnetic field is present. So electrostatic energy has been converted into magnetic energy. Fine. Now what will happen after the discharge of this is complete, capacitor is complete, we'll be having certain terms we have studied in EMI. There will be introduction of Lenz's law. After the discharge of the capacitor is complete, the magnetic flux which is linked with the inductor, that decreases. Current decreases, magnetic flux will decrease. Remember we did this, phi is directly proportional to I. So that will also happen. So same thing will happen as the current decreases, the magnetic flux linked with the inductor decrease. So it induces the current in the same direction. There will be induction of current. So here, let's say current I is flowing. This is inductor, this is capacitor. Current I has started flowing back as the earlier current. Now, this current, it persists, but with decreasing magnitude definitely, and charges the capacitor in the opposite direction this time. Here, initially capacitor electrostatic energy was there, it transferred it into the magnetic energy. Now what will happen, it will start to discharge it, recharge this back, recharge the capacitor back. So now the strength of the magnetic field that was present, it will be now lesser, not that greater the way it was previously, and the energy in case of capacitor will also not be zero. It will also be having certain value. Now what will happen? It has started to begin its recharging journey. Now what will happen? Magnetic energy of the inductor begins to change into electrostatic energy of the capacitor. And this process continues till when? When your capacitor is fully charged. When your capacitor is fully charged. So it means if this is the circuit, this is the inductor, this is the capacitor, this is the this is magnetic energy, this is electric energy, this is inductor, this is capacitor. So what has happened now? Now since after we had started to recharge it back, so capacitor now begins to get fully discharged, fully charged now. So your capacitor, now definitely this will occur that the polarity will be changed. This will be here minus, this will be plus. And magnetic field here now will be zero because we have emptied it, so electric energy becomes zero. Now what will happen? Again, capacitor will begin to discharge it. All the process continues, same steps. Same steps continue. And when they'll continue and when they'll reach the step back, what will happen? The polarity of the capacitor begins to regain. Now, C class. Try to look at it simultaneously. C class, from where we had started. This was initially our circuit, and what was the magnetic field? This was half Li square. This was initial case. There was electric energy present in our circuit. Then the capacitor begins to discharge itself. The capacitor got discharged. Fine. Capacitor got discharged, and so because of the presence of this current, there was magnetic field. And in the whole lesson EMI, we were studying this only, that how because of the presence of current, we are able to find magnetic field. This was the case that we were studying in electromagnetic induction. So obviously here what happens? In this case, your magnetic field lines are coming. Magnetic field lines are coming. There will be now magnetic energy is there as well as electric energy. Some of the electric energy is there, but the magnitude has been low. Fine. What happened in the first step? Capacitor and inductor were connected. Capacitor was fully charged with electrostatic energy. Second, capacitor begins to discharge itself. Some current flows through the inductor, making the magnetic field. Magnetic energy and electric energy both are now present. This is the second step. Now the third step. Finally, capacitor got emptied. This is an empty capacitor. This is an empty capacitor and all the current has gone. This has been discharged. This is now empty, and because of the presence of so much amount of current, there's a huge magnetic field presence, and because of which we have only magnetic energy. We do not have electric energy. Fine. Then what happens? Then again, recharging of the capacitor begins. Process continues till when? When the capacitor is fully charged. So this continues. So what happens? There's a slight decrease in magnetic field, but since magnetic field are present, so magnetic energy is also there. Capacitor begins to recharge itself. So there's energy of capacitor also. So there will be electric energy as well associated over here. Lastly, what happens when the capacitor becomes fully charged? So if inductor becomes fully discharged, so you have no magnetic energy over here, but you have electrostatic energy. Then again, what will happen? This was what? See, this was your step 3. And this was your step 4. This was your step 5. Fine. So now what happens? After this step, 6th step is this only. Capacitor will again start to discharge itself from the 2nd step. Then 3rd step, 4th step. Ultimately, the polarity that was reversed, no. The polarity is exactly the same. From where we had started, we have reached back. So what has happened, class? Do you notice there's an oscillation of energy between the magnetic field and electric field? Electric field's energy and magnetic field's energy. There's an oscillation between them. Did you understand? Is this clear?
Yes, ma'am.
This oscillation that is occurring between the magnetic field energy. See, electric energy was high here. Both are equal. Then magnetic field is high. Both are equal. Electric energy high. All these things. These are what? All these are directly. These are simply oscillations that are occurring. So this is meant by LC oscillation because it is occurring in the L and C circuit. LC circuit means your inductor and capacitor circuit. Understood? Any doubts from here? I'll just tell you what is, I'll write down the definition of LC oscillation first. See, when a charged capacitor, this is a part of your course, so pay attention to this. So when a charged capacitor is allowed to discharge, this only happened, no? Initially our capacitor was charged. So this, when this is allowed to discharge, when a charged capacitor is allowed to discharge through a non-resistive inductor, or through an inductor also you can write, through a non-resistive inductor, what happens? Electrical oscillations of constant amplitude and frequency these are produced. Fine. So these oscillations are known as LC oscillations. These oscillations are LC oscillations. Got it or not? All All right. Starting from you, Atif. Atif, tell what was the first step that occurred here? What was 1 over here? Yes, Atif. Let's start from you. First step, what happened?
And step 1, the capacitor is fully charged and the inductor contains no energy. There is no current flowing through the circuit.
There is perfect. So there is no current flowing through the circuit. Electrostatic energy is full. Magnetic energy is not there because no current is flowing. So no magnetic field is produced. This is the first thing that is occurring. Akifa. Akifa, can you unmute yourself? Okay, Akifa's network issue. Fine, Akifa. Next, Fatima. Second step, what happened then? Yes, Fatima. What happened next in the second step? Just look at the figure. Try to tell. What happened to the capacitor's energy?
It got discharged.
It got discharged. So current flowed or not in the circuit?
It flowed.
Current flowed. Because of current there was magnetic field. So we had magnetic energy. So now at this moment we have both electric and magnetic energy as well. Both the energies are there. Fine, Hamza. What happened next? Look at step 3. Yes, Hamza, what happened then? What happened to capacitor? What happened to inductor? Any difference in energy now? Hanifa. No, Hamza is there. Hamza, are you able to hear? There, Hamza? Okay, next, Hanifa. How much have you understood? Step 3. What happens to the capacitor? Discharged, fully discharged, emptied. What happened to the capacitor, Hanifa? Yes, it's written in front of you, Hanifa. Okay, your audio is not working. Hamza, what about you? Unmute yourself, Hamza. Capacitor is empty. That I got. What about the magnetic field? What about electric energy? Magnetic energy, electric energy, Hamza. Look, everything is in front of you only. Okay, fine. Who's next, Hiba? What happens to capacitor? Capacitor is now fully emptied. All the because of the current. Now, what happens to the electrostatic energy and magnetic energy? Is there any difference, or it's the same as that of previous case, step 2? Is this same like this, Hiba? It increases. So what increases? Electric energy increases or magnetic energy increases? All those who are able to unmute themselves, please unmute and answer. Because this wastes a lot of time. If people type first and the message is received over here, what happens? Is it the magnetic energy which has increased or electric energy, Hiba? Which energy you are referring to? What is it over here? No idea. Josefa? Which energy increases now? Once capacitor has been emptied, which energy increases now? See, can't you people directly see over here? It is directly written. Capacitor has been emptied. Now, once the capacitor has been emptied, a lot of current has flown because the whole charge that was there is not present anymore in the capacitor. Because of it, we are having large amounts of magnetic field, because of which magnetic energy exists and no electric energy is there. Krishna explains step 4. What happened next then?
Ma'am, the capacitor gets charged and the magnetic field, the energy gets decreased. And in this process, the electric energy increases.
Electric energy, perfect. See, slightly now what is happening? Capacitor is begin to recharge itself. Again, the capacitor is recharged. And so what happens now? Magnetic energy will decrease, electric energy will increase, because initially, right before that, we didn't have any electric energy. That will occur. Who's next after Krishna? Kulsum. Kulsum, what happens next? What happens to the polarity of capacitor? Is it the same, different, opposite? What? Kulsum. Tara, can you explain step 5?
The polarity of the capacitor becomes opposite.
It will be opposite. And what about the energies?
The electrical energy will increase.
Exactly. See, it was very simple. You just have to read. Everything was written on the screen only. I just wanted you people to dictate it. Fine. So I hope now it's clear, because everyone has repeated and I have also repeated. This was the third time that the repetition was done. So just note it down. Any doubts in here, ask me. I think here you have to note it down. Yes. Please put the heading as LC oscillations. I didn't put the heading. Write the heading as LC oscillations. Pick it. See, mathematical treatment of oscillation means what's the formula for it. So it can be asked to you to show whether the capacitor, when a capacitor is discharged through an inductor, then it is oscillatory or harmonic. So to find its frequency, you have to find its frequency. That can also be asked. So frequency is same. Frequency of LC oscillation is same as that you have studied in case of resonance. What was the formula of frequency in case of resonance? Angular frequency in resonance condition, Akifa. What was the formula of angular frequency for resonance? We had a term omega is equal to, what was that, Akifa? No idea. Are you there, Akifa? See omega, Akifa. This is 1 by under root LC. You people are not at all revising. 2 pi f. No, 2 pi nu is, this is the normal angular frequency. That's the normal angular frequency. For resonant condition, this is omega is equal to 1 by under root LC. This is the formula for it. Please start revising. So this is inductor, this is capacitor. Now current is what? Since the current is charge is decreasing, so current increases. Your current is actually minus dq over dt. Minus sign, just we are adding minus sign to show that the charge is decreasing. Because in the capacitor, this only happened, no? In the LC oscillation, the charge got decreased. So same thing will occur over here also. I is equal to minus dq over dt. And EMF also we know, EMF is minus L di over dt. This is the induced EMF. Induced EMF across an inductor. So potential difference across a capacitor, potential difference is what? This is Q divided by C. Now, if you apply Kirchhoff's loop law in over here, if you look at this, you just have to add all the potential difference. So potential difference across the inductor is minus L di over dt, and potential difference across the capacitor is what? Q by C. So total potential difference will become what? This is potential difference across inductor plus Q by C. This is potential difference across capacitor. This is equal to what? This is equal to 0 using Kirchhoff's loop law. So even if you transport it on the other side, this becomes positive, or even you can just do one thing. Bring this, multiply and divide everything by L. Just divide L by L on both the sides. So here if you divide by L, if you divide this term by L, what happens? See, before we do that, see, di over dt, I want to write it in terms of charge. So you know charge is what? Minus dq over dt. Here we are adding this minus sign to represent that it is decreasing. So di, when you have to write, if you divide it by dt, this becomes double differentiation of charge. Fine class, you can write it in this term also. So when you have to show this in your exam, mention this step also in bracket. So what does it become? This minus will become plus, and instead of di over dt, I'll write d square q over dt square plus q by c. This is equal to what? This is equal to 0. Now multiply L on both the sides if you do this. See, L is here. If you divide it by L, divide by L. L is what? L is the self-inductance. See, if you divide by L, what will happen? If you divide by L, from here L will go up, L will vanish, L by L, it will get cancelled. So d square q over dt square. And if you divide L over here, an additional L will come. This is equal to 0. Now, this 1 by LC that you are coming, we write it as a constant known as omega square. This is a random constant which we write. So equation becomes what? dq square. Non-random constant means you know its angular frequency, and we already know the relation that I told you in the starting only. But proof involves this. This is what? Omega square q is equal to 0. If you people are able to recall, in class 11th, you have done this exact equation in terms of displacement and time. That was the second order equation. This is known as the linear differential equation. Linear differential equation. Linear differential equation means what? You call this equation at this step, you call it as linear differential equation. In case of oscillations and wave, you had a lesson, remember in class 11th, waves and oscillation. There also you get exact this kind of equation where you have omega only. Where from there you get omega is equal to under root k by m. So similar thing just for LNC. LNC means for inductor and capacitor. Fine. And from here we say omega square is equal to 1 by LC, omega is equal to 1 by under root LC, or linear frequency is 1 by 2 pi under root LC, like this. All right, class. So this is the mathematical treatment of LC oscillations. Just note this down as well. Just text done when you have completed. Done in the chat room. Just text me when you have completed. And what about others apart from Fatima and Krishna? Done or not? All right, yes. So, see, I'll stop here. I'll not teach further. We'll complete oscillations, LC oscillations, certain questions we'll do, and transformers is left. That we'll do on Tuesday only now. So, be prepared for the test for on Thursday, 8th of September. You people are not revising now. So, please revise, come and revise it. And on Tuesday only, we'll be having revision also of this chapter, and then we'll do the leftover questions. All right, whatever you are having doubts regarding the assignment from anywhere, just let me know. Otherwise, just stop here today. Fine? Okay, thank you so much. All of you can leave now.
Thank you, ma'am.